All right, so looking at this is, first of all, there's two types of electrolytic cells. There's galvanic and electrolytic. Which one would this be and why? There's many reasons. First of all, what do we know about galvanic? Very good. So galvanic is spontaneous or non-spontaneous? It is thermodynamically favorable. So we're going to have a positive voltage, right? Or which is equal to positive E naught. We need a salt bridge. We have a voltmeter, right? We have two containers and all that good stuff. So this is the galvanic cell. The easiest way to tell is one, it says voltmeter, and two, you have a salt bridge. Those are the easiest ways to tell. Okay. Now, in a spontaneous reaction that occurs when the cell operates, the Oh, that confused me for a second. All right, these are the conditions. That makes a little more sense. That kind of confused me. A 50 milliliter sample of a 2 molar cadmium nitrate is added to the beaker. Added the beaker to the left. All right. First of all, since we know this is galvanic, so what I want you to do is put a positive, or put plus volt over here. Does that make sense? Why? Because since it's galvanic, a voltage is a product. We're going to produce it. And then this just kind of works just like with Chatelier. A 50 milliliter sample of a 2 molar cadmium nitrate. Now, what do we know about cadmium nitrate? Very good. So it's just really, we're really focusing on the 2 plus ion, right? So where am I adding that to? Yep. I'm adding that to the product side. So if I add to the products, how am I going to shift? Towards the reactants. So what's going to happen to your voltage? Your voltage is going to go down. Which quiz is this? Quiz 11. This is voltage. Okay, just making sure. All right, so the answer there should be B. The voltage should go down because we're shifting away from the products, right? All right, number 2. The silver electrode is made larger. The silver electrode is made larger. What do you think happens? We're just basically swapping the size of how big this silver electrode is. But here's the interesting part. Here's what you got to focus on. Because, first of all, what is silver going through oxidation or reduction? And how can you tell? It's going from +1 to 0. So it's going through reduction, right? So it's going from 1 to 0. That's going down. That's reduction. All right. What happens to the cathode? It gets bigger. So do you agree that these ions are going to be jumping onto that silver bar? So what that tells me is, who cares how big that bar is, right? So because that we're actually sticking ions on the bar, is that going to have any effect on the overall voltage? Not a dang bit. So it's actually going to be D. But what if the question were the silver electrode is made, the cadmium electrode is made larger? What would that do? Do you agree that cadmium is going through oxidation? Which what happens in oxidation? It loses. So we're having ions fall into solution, right? So if the cadmium bar was bigger, could we actually throw more ions into solution? So could it run a little longer? That means the voltage would go up. Does that make sense? Okay, so those are some things you just kind of have to play with. All right. B, the salt bridge is replaced by a platinum wire. Basically, we take the salt bridge out and we just stick a wire in. What happens? What's the purpose of the salt bridge? It maintains what? Remember, it maintains neutrality. So So if we take the salt bridge out, will it be neutral anymore? You should have a bunch of ions flooding the solution, right? So what's going to happen to the ability for it to remain neutral? It stops. So what happens to the battery? Stops working. So what's your voltage? 0, exactly. So it's got to be C right there. The current is allowed to flow for 5 minutes. Do batteries, when they run and run and run, do they get more powerful? Do they get less powerful? Do they stay the same? When batteries run, batteries ever die. So what happens to their voltage? Over time, it slowly decreases. So that's got to be the answer there. So when batteries are allowed to run, they slowly decrease. Why? Do you have only a certain amount of electrons that you can pull through that wire? Once you run out of electrons, you're done. There's nothing else you can do. Okay. B, the molarity of the silver nitrate is changed to 0.5 molar. So basically what they're doing is they're changing this concentration to 0.5. Now we got to think about what's going on in that beaker. Aren't those silver ions being pulled out of solution to stick to that bar? Well, what did you technically do to the solution from the original? Then we have the concentration. So that means you have half the ions. So if you have half the ions, do you have more or less current that can flow? Less. So what's going to happen to your voltage? It should go down, which is B, right? Another way to look at it is Le Chatelier. If I change the concentration, what part of that reaction am I altering? Specifically. The silver metal or silver ion? So, if you just look right here for just a second, look up here. Am I changing that? Am I adding or am I taking it away? Taking it away. Well, when I take that out, what happens to your voltage? I'm shifting this way, right? So what happens to the voltage? It's got to go down. Exact same way to think about it. You're thinking about it physically versus analytically. Both ways work. Does that make sense? Okay, good. All right. We did these. I just want to run through these one more time just to make sure. The energy required to convert ground state to positive ion. What did we say that was? Yep, ionization energy. The energy change that occurs in the conversion of an ionic solid. Now, how are ionic solids set up? As a lattice, right? So it's taking an ionic solid and it's spreading it into a gas. So that is lattice energy. The energy in a chemical or physical change that is available to do useful work, well, that's free energy. That's a bit energy that we have to work. The energy required to form the transition state in a chemical reaction. Well, remember, transition state is where on a thermo graph? The very, very top. Well, what part of the graph is that? That's the activation energy part, so it's got to be A. Does that make sense? Okay. Temperature is the measure of the kinetic of the average of this energy. Remember I told you this, that kinetic energy is equal to temperature. They have to be directly proportional. Okay, all right, so let's look at the next one. Refer to aqueous solutions containing a 1-to-1 mole ratios of the following pair of substances. Assume all concentrations are 1 molar. The solution with the lowest pH. Now, when it says lowest pH, what is it referring to? Very good. With the most acidic, which is the most concentrations of H+, right? So, all right, let's look at the next one. Most nearly neutral. So you're looking at H plus is equal to OH minus. Now, 3 and 4 you guys don't really understand. But a buffer of a pH greater than 8 is, you're going to be dealing with a strong base and the conjugate acid. And then buffer of a less than pH, less than 6, you're going to be dealing with a strong acid and a conjugate base. And then the solution with the highest pH. What are you looking for there? So it's the most basic And there's two ways to look at it. It's the least H plus, right? But it's the most what? OH minus. Okay, so let's kind of look up there and see what we have. Does anybody see? All right, what do we notice about E? About those two compounds. What do you notice about those two? They're both weak. So this is quiz 12. I just want to make sure I'm on the right page. All right, so since they're both weak, what do weak and weak do? They cancel out, which would make them what? Which would make them what on the pH scale? About neutral, right? So there's your neutral one. So E is going to be the most neutral solution. I can't. The solution with the lowest pH. All right, can it be A? It's definitely not A because you have a weak base in the beginning, right? Could it be B? You have a weak acid, so it's potential. What about C? You've got a strong acid and a salt, right? And then D, you have a weak, or excuse me, you got a strong base. So that kind of throws it out there. So which one's it going to be? The lowest pH, most acidic. It's going to be C, right? Because of that strong base. All right, well, let's look at the last answer then. The solution with the highest pH. Well, there was only one strong base on there, so what would it be? D. Do you agree? Okay. Well, now that leaves us with a few other things. I made a mistake of what I wrote right here. And this is why buffers are my weakest part. Where it says buffer of a pH greater than 8, please write that as a weak base. And number 4, please write that as a weak acid. I made that little bitty mistake. So now it should make a little bit more sense of what happens. Is a buffer with a pH greater than 8 is going to be a weak base and a conjugate acid. Which one of those do you have a weak base and its conjugate acid? Remember, what does NH3 turn into? Do you see NH3 and NH4 plus? That's a weak base and its conjugate acid, right? So that's going to be letter A. Does that make sense? And then the other one, the phosphoric acid is H3PO4. It's an acid. So what do acids do with hydrogens? They lose or gain? They lose, right? Which would make this thing turn into H2PO4 minus. Do you see that up there? Which one is that one? That's B, right? Do you see kind of how that works? But the thing about it is, where did this Cl come from and where did this Na come from? That came from the solution, right? Basically, they just paired it up so it's not charged. Does that make a little bit more sense? Okay.
It made it look like they were
Yep. All right, looking at the next one. 6 is a gas at standard temperature. That should be really easy. Is a gas. It is fluorine. So that's E. Reacts with water to form a strong base. There's only one possible choice. Lithium. Right? Because lithium hydroxide is a strong base. Is a liquid at standard state. There's only 2 liquids on the entire periodic table. We know mercury. What's the other? Bromine. Okay, so that's going to be C. Is radioactive. Duh. I hope you would know that one. That is D. And then the element with the greatest paramagnetic properties. Well, it only leaves one. Matter of fact, let me just make sure that I'm not crazy in this. Which one is this? This is quiz 12, right? Hold on. It is B, yeah. Let's talk about why that is. If you look at where nickel is, nickel ends as 3D, 1, 2, 3, 4, 5, 6, 7, 8. It's 3D8, so when you do it, it's 1, 2, 3, 4, 5. And as a matter of fact, y'all could probably draw this down here below it. And so I need 8. So 1, 2, 3, 4, 5, 6, 7, 8. Remember, paramagnetic means what? It needs more electron to fulfill its pairs. Well, there's one missing and there's one missing. Does that make sense? Okay. But if you look at lithium, and I just want to show you this, if you look at lithium, lithium is 2s1. Well, it's only missing how many electrons? It's just missing 1. If you look at bromine, bromine is 1, 2, 3, 4p6 or 4p5, right? So 1, 2, 3, 4, 5. How many is bromine missing? Just 1. So does that make sense? And fluorine is the exact same as bromine because they're both halogens. So the reason with the greatest paramagnetic is because it's missing 2 electrons. And then we wouldn't even talk about uranium on that. Okay? All right, this is a phase diagram. You're going to laugh when I say this. We call these the butt cheek diagrams. Because if you look at it, it kind of looks like a butt cheek, doesn't it? And this is going to get even weirder. What comes out of your butt cheeks? A gas. Sorry. What would a state of matter be at really, really low temperatures? Solid. What happens to state of matter is at higher temperatures? Liquid. So that, you with me? So solids, liquids, and gases. This is a phase. This is a phase diagram, but it's called the butt diagram too. All right. I know it's rough. So number 1, if the temperature increases from 10 to 60 at a constant pressure of 0.4, which of these processes occur? Now, this is how you have to read this. So we're starting at 10 and we're going to 60, right? But what pressure? Where are we going to be on the y-axis? Is it where, according to those 3 lines? Above the first one or below the first one? You agree we're going to be right below it? So we're starting at 10 and we're going to 60. So you agree we're going to follow that green line. So what states of matter are we converting from and to? Yep. So we're going from a solid to a gas. What process is that? Sublimation. So that is the answer. Do y'all see how I did that? Okay. I'm going to change colors on this one. I'm going to go to a orangish color. If the temperature decreases from 110 to 40 at a constant pressure of 1.1. All right. So we're going from 110 to 40 at 1.1. Do y'all agree? All right, so where did we start? What state did we start at? Started at a gas, because we started at 110 and we went in to 40. So we went from a gas to a liquid. What state of matter is that? Or what change is that? Gas to liquid? Condensation, very good. So that is going to be B. If the pressure increases from 0.5 to 1.5 at a constant temperature of 50. All right, this is going to be a blue color. So we're staying at 50, and we're just going to go up to 1.5. So what do we convert from and to? Gas to liquid. So what phase is that? Or what changes that? Gas to liquid. It's condensation again, right? Okay. All right, if the temperature decreases, I'm going to change this to a purple color. If the temperature decreases from 50 to 10 at a constant pressure of 1.5. So we're starting at 50 and we're going to 10 at 1.5. What did you go from and to? Very good. And what is it called when you go from liquid to a solid? Freezing, very good. So to see how these works, they're not hard. You just kind of got to look at them and figure them out. And the last one I'm going to do, I'm going to make it like a light ice blue color. If the temperature decreases from 30 to 10 at a pressure of 0.5, what is that? So we're going from 30 to 10 at 0.5. So what are we going from and to? Gas to solid. What is that called? Deposition. And so that is answer choice D. So do those make sense? It's you just kind of got to figure out how it plots. But would you have known any of those if you did not know the butt diagram? It's weird, it's gross, but always remember the gas goes at the butt cheeks. Okay? It's just the best way to remember it. Ooh, these are tough. I'm going to be honest with you. If you see anything with sigma or pi, I have no idea. Now, we do know one of these. Which one of these has the shortest bond length? Actually, I was... Oh, duh. Let's look at this analytically. Do you agree that F to F is a single bond? Do you agree that O to O is a double bond? And N to N is a what? What do we know about triple bonds? They're the shortest, right? So that is going to be C. Which one of these has the largest bond dissociation energy? Just kind of talk these out loud. Well, the more bonds. If I were to ask you to break through those three, which one would be the hardest to do? Why? That triple bond, right? Okay, the more bonds, the harder it is to break. That makes a lot of sense. I'm going to be 100% honest with you. I have no idea what a bond order of 2 means. I have no clue what that means at all. I'll just go ahead and give you the rest of these answers. It is C, D, C, D. If that helps any at all. Okay. Next page. Has an average atomic or molecular speed closest to that of N2. Now, here's what you have to understand. Speed is proportional to mass. So, if the equivalent masses have equivalent speeds at equivalent pressures and temperatures. So, what is the mass of nitrogen? Now, that's N2, not just 1. 28.02. We got to figure this out. Which one of these has a mass closest to 28.02? Well, we know oxygen is 32, right? All right, what is Xc? Xc is 131. Well, that's definitely not it. Ne is 20.8. CO is 12.01 plus 16, which is... Say 20, what?
Yeah, 12 plus 16.
28? Well, that's pretty dang close, isn't it? Okay, so it's actually 28.01, so that's our answer. So it's got to be D. Okay. Which of these has the greatest density? Now, what do we know about density? Mass divided by volume. Well, which one of these? What is 14 plus 16? 30, right? Well, which one of these has the most mass? Xenon, which would be B, right? So it has the greatest density. Has the greatest rate of effusion through a pinhole. Effusion is like a cologne or like it's pressurized, so it's the small gases get out. So it has to do with the smallest and lightest. So who would that be? Would be neon. Let me just double check, make sure. I keep forgetting where we are. What quiz are we on? 14. 3 is A. It is neon. Very good. All right. The most polar. That's interesting. Which one of these has the greatest differences in electronegativity? D, very good. And then has the density closest to 1 gram per liter. That's an interesting question. The answer there is D. And I can't quite tell you why that's true. That is interesting. I don't know that one. All right, next group is used to explain why iodine molecules are held together in a solid state. Now, iodine molecules. So when it's referring to a molecule, that's referring to an IMF, right? Okay. Is it a hybridization? It's not even ionic bonding. What is resonance? Resonance is the same molecule, different structure. Okay? Could this even have hydrogen bonding? Nope. Well, what is iodine? Remember, it's I2. So is that polar or non-polar? So what does that have to make its forces be? London dispersion, right? So that's got to be what? E. Is used to explain why the boiling point of HF, so we're talking about boiling point of HF is greater than the boiling point of HBr. Boiling points are always an IMF issue. So I would make that little note out to this side, that boiling point equals IMF. The stronger the IMF, the higher or lower the boiling point. The higher. So HF has a higher boiling point. Well, what does HF have that HBr doesn't have? Hydrogen bonding, very good, so it's A. Okay, is used to explain that the fact that the 4 bonds in methane are equivalent. Does that have anything to do with hydrogen bonding? Ionic bonding? Van der Waals forces. So we've narrowed it down to hydrogen bonding and resonance. But what is resonance? It's the same molecule, different structure. So hybridization is to explain why they're equivalent. Okay. So it's B. 9 is used to explain the fact that the carbon-to-carbon bonds in benzene are identical. That is D, resonance. Same structure, different shapes. And then 10 is used to explain the fact that noble gas can be liquefied. That's an interesting one. Noble gases. What kind of forces do they have between each other? They polar or non-polar? They're non-polar, so what do they have to have? Got to have an LDF. Now, what does it mean to go from a gas to a liquid? What's technically happened on the molecular level? They're getting closer, which means they can form a force between them. And so if something is liquefied, that means an IMF has occurred. Well, if something is non-polar, the only IMF it can have is a LDF. That makes sense. So if you think about it in terms of states of matter, a state of matter change only occurs because an intermolecular force has changed. Okay, all right, last set. All right, so we're going to do just part B of 15. All right. Used to explain why some oil will dissolve in water. Ooh, these are different. All right, we're not quite sure, so let's move on. Used to explain the trend in melting points of the halogens. All right, here's the thing about halogens. They're diatomics. So when you have melting point, do you agree that melting point is a phase change? Is a phase change in IMF? All right, so you got to figure out what kind of IMF a diatomic would have. F2, Cl2, Br2, I2. They're all non-polar, which means it has to be a what? It has to be an LDF. So that is why it is. And again, that's tying a lot of pieces of the puzzle together. So it talks about melting points. Melting points have to be IMFs. Well, diatomics are non-polar because halogens are diatomics, which are non-polar, which has to be an LDF. Okay, number 8, used to explain why water is a liquid at room temperature. What kind of, all right, do you agree that liquid is a phase? What do we know about phases? That has to do with IMFs, right? Well, what is your IMF for water? Hydrogen bonding. There you go. So anytime you see something about phases, you got to think intermolecular forces, especially if it's a molecule. All right, explains why xenon can form compounds with lighter noble, while lighter noble gases do not. Now, forming compounds has to do with things outside of the effect of with bonding, and it has to do with how all the things match up. And so I'm just going to go and tell you that this has to do with hybridization, because yeah. And so if you think about it, compounds have to do with bonds, and bonds are how electrons attach. And so it's got to be hybridization. Okay, then finally, 10 explains why iodine is a solid. Again, what do we know about solids? That is a phase, so that has to do with IMF. So what does that tell us? This is 15. And we know that iodine is I2, right? Well, iodine has to be non-polar, so what does that tell us? It's an LDF. Does that make sense? So it's got to be A. All right, so let's go back up to number 6, because I know we didn't answer that one. The correct answer is B, because oil. What do we know about oil? Is it polar or non-polar? Oil is non-polar. What do we know about water? It's polar. So, polar things have these things called dipoles. If it's non-polar, can it have a dipole? Well, if you go back and you look, the only two things left are dipole to dipole interactions. Will oil have a dipole? So non-polar things have no dipoles. What does induced mean? Very good, it's forced. So can oil sometime be forced to have a dipole? Yes, and that is why. Because remember, electrons are constantly moving, and so at any moment, it can be forced into that dipole. And so that is why it is an induced. It's forced. Because if you mix oil and water, isn't that's forced? You'd have to force it to happen. That's what induced means. Okay? Does that make sense? All right, so is that worth to stay? Okay, good. I wish I had done it as a PDF earlier. What's today's date?
29.
Thank you.
See, IMFs and bonds are just the one thing that I never really understood.
Yeah.
I don't know why.
Because you weren't taught.